Okay, we're nearing the end. Just a few more things. In 6.4, we're putting it all together. Essentially, it means some miscellaneous example, which doesn't aim to cover every single type of question, but we have already taught all the concepts needed to solve all types of vectors questions. So from example 13 onwards is all exposure type of problem. They mostly are past year paper problems. We want to expose you, and that's that. There are a lot of questions in self-practice. Please go and try them. Alright? But before we do example 13, let's take a look at one last bit. We have done distance between two parallel lines. We have done distance between two parallel planes. Now we are talking about distance between plane and line. Alright, so now again, inherently it must be parallel lah. If it's not parallel, there's no distance to talk about, because I have a plane, I have a line that's not parallel, then there's no distance to talk about because they intersect at this point. End of story. So it must be parallel. The simple solution is this. All I need is I take a point on the line. Okay, it can be reduced to a problem of a distance between a point P on the line and the plane. So I call this P. So I do not want to go through how to find a distance between a point and a plane because we have done it before. Alright? But I do want to answer this question. What can I do it the other way around? Because this is the distance, right? I can find distance between point and plane. Can I just take a point on the plane instead? That means instead of like that, I find this is the line. I take any random point P. Now in 2D, it's not very obvious that it's wrong. I must tell you if it's wrong because it cannot be found. In 3D, look at the camera now. Look at the camera head now. You see, this is a line and a plane. Yes. I want to find shortest. Let's say the shortest distance is just like that. It's very near, right? Here and here. Correct. But if I pick any random point here, very far away here, I mark it with X. Can you see the X? Yes. So you can see the X here. This is on the plane. X is still on the plane. And the point and the line is like that, parallel to the plane. The line is not intersecting. If I take any random point there, if the distance between that point and this line is so far, it's not the distance between the line and the plane. The line and the plane is just this short distance. So we cannot just take any random point on the plane. Back to the screen, it must be a point on the line. Because if it's a point on the line, it's okay. Because now I have plane, I have a line. Any point on this line is fine. Point to plane is just this short distance. All good? So we've done with that. I'm not going to do the calculation, but I just want to emphasize that it must take any point on the line to the plane. So let's go to example 13, putting it all together. All right, first example of everything putting it all together. Let's read the question. I have two planes. First part, verify that 1, 3, minus 2 lie on both the planes. Simple enough. You just substitute X, substitute the Y, substitute the Z. Your left hand side eventually equals to 2, which is the right hand side. We're done. Same thing. If you want to show that it lies on pi 2, you just substitute X equals to 1, Y equals to 3, Z equals to minus 2, eventually equals 14. Done. So the solution is on the next page here. So this is done. I think this is not difficult. Now let us tackle the next part of the problem. The next part of the problem asks us to explain why the line of intersection L1 actually is parallel to 1 minus 1, 4. So look, Let's see, I try and draw two planes now. Pi 1, pi 2. Okay, not bad line. Okay, pi 1, pi 2. So, this is the line of intersection. You want to show that this line of intersection is parallel to 1, minus 1, 4. Essentially, you want to show that the direction vector of the line of intersection is 1, minus 1, 4 lah. Right? Yes, the direction vector of the line of intersection L1 is 1, minus 1, 4. How do you find the direction vector of intersection between two planes? Now, this direction vector, this line, surely is perpendicular since it lies on pi 1. Right? This line lies on pi 1. Surely the direction vector should be perpendicular to normal 1. Right? So I'm going to write this 1, minus 1, 4. I take this dot, the normal of pi 1, 3, minus 1, minus 1. I say one more time, maybe I would write it like that. This is the normal. This is the 1, minus 1, 4, which is what they want. This is the normal of pi 1. You take dot product, you realize that this is 3 plus 1 minus 4 equal to 0. What does equal to 0 mean? Equal to 0 means that this normal vector is perpendicular to 1, minus 1, 4. Next, I will take 1, minus 1, 4 again, dot the normal of pi 2, which is 1, 5, 1. I get 1 minus 5 plus 4 also equals to 0. What does it tell us? It tells us that now this vector is perpendicular to the normal of pi 2. So the conclusion lies here. This vector now is perpendicular to the normal of pi 1 and pi 2, which means this is parallel to pi 1 and pi 2. So which means this vector is parallel to the line of intersection between pi and pi 2. And I think this diagram tells us a little bit more than words itself. Word can only mean like that. This is pi n2. Okay. What we have shown earlier, what we have shown here is that somehow I take normal vector, dot this vector, I get 0. Means what? Means these two are perpendicular. Means what? Means 1 minus 1, 4 actually is parallel to pi 1. Next, this n2. I took 1 minus 1, 4 dot n2. I also get 0. It means that 1 minus 1, 4 is perpendicular to n2, which means 1 minus 1, 4 is parallel to pi 2. Good. That means 1 minus 1, 4 actually is parallel to pi 1 and pi 2. That means it must actually be the direction vector of the line of intersection. That's all. Okay? So we have done with the first two sections. The next section, what did they ask us to do? Part 1, you read your question. I'm not going to turn to that line. Show that L1 and L2 are perpendicular. All you need to do is, this is the direction vector of L1, which is here, 1 minus 1, 4. This is the direction vector of L2. You take dot, eventually you show there is 0, therefore the two lines are perpendicular. Done. Next, let's go back to the question now. So we've done this one. Show that L1 and L2 are perpendicular. We have done the verified. We have done the explain. Next. Find the coordinates of the point of intersection P between L2 given, everything given, and pi 1. This is easy peasy. Intersection, I think even vectors 5 in CT1, you have done it before. Just solve simultaneous equation. Okay, later we show that. And last bit, show that the perpendicular distance from P to pi 2 is this. So now we talk about distance. Okay, let's deal with the part 2. Yes. To find the intersection between line and plane, all you need to do is to substitute So we will substitute equation of L2 into pi 1. What is the equation of L2? Is given, which is 108 plus S 1 minus 3 minus 1 dot 3 minus 1 minus 1 equals to 2. Alright, this part is the equation of L2. You substitute into equation of pi 1 equals to 2. Objective is to solve for S, and H is the next line here. Okay, you get S equals to 1, you substitute back here, you will get the coordinates of P. I think that's easy, intersection between a line and plane. The very last part now, I want to find the perpendicular distance between P and the plane. P has coordinates, so I know already, this is 2 minus 7, 3, 7. And I'm only interested in the perpendicular distance, that means I want to find this distance. The shortest way, the fastest way to do this is to make use of the idea of projection. Because I'm not interested in F. The question didn't ask for coordinates of F. I don't need F. Yes, I actually don't need F. So I only need the shortest distance. I will take a point A. This is 1, 3, minus 2. Or any other point that can satisfy this thing. Any other point. 1, 3, minus 2 is just a possible combination to get 14. Correct? 1, 3, minus 2. But there are many, many possibilities. But let's decide on A, 1, 3, minus 2. I take A, PA. Yes, PA dot the unit vector of the normal. Yes, dot the unit vector of the normal. I will project PA. Sorry, I project PA onto the normal, which is essentially this PA dot n hat, right? PA dot n hat, which is minus 1, 6, minus 9 dot n hat is 1 over root 27, 151. Then you will get this. Alright, and you take dot, blah blah blah, you will get a mod minus 1 plus 30 minus 9. So over root 27. You will get 20 over 3 root 3. That's that. That is the final answer of example 13.